In this lecture, we're going to look at more quantitative ways to think about chemical energetics and how energy can kind of be transferred in between species of a chemical system. Okay, so what I want to talk about to start is the idea of a huge branch of science called thermodynamics. So thermodynamics is sort of the study of how energy / heat is transferred in various systems. This is a really beautiful branch of science. It's one of these branches of science that we've gotten so good at that we're able to just kind of predict so many things. And the idea of a law of the physical universe really shines through in the idea of thermodynamics. The laws of thermodynamics seem to hold up over and over again, really showing how well this field has developed. And it's become incredibly useful in our engineering efforts, and really is a big reason why a lot of kind of our modern engineering efforts have been so successful. Okay, so thermodynamics deals with stability. So when we're talking about the word thermodynamics, I want the idea of stability to come into mind. There's a separate field called chemical kinetics that we'll talk about a few lectures from now. And chemical kinetics is different. I mean, it's certainly related, but it's different enough. And with chemical kinetics, I want you to think about speed. And so anytime you're ever thinking, like, as you're trying to grapple with understanding basic ideas of chemistry, anytime you're thinking about how fast or slow something is occurring, that has to do with chemical kinetics. We're not going to talk about kinetics right now. We're going to talk about thermodynamics instead. So with thermodynamics, again, we're thinking about stability. And stability refers to relative energy. Relative energy. Okay, so we can quantify the energy of a system using the term heat of reaction. So quantifying the energy of a chemical process, we're going to use a term called the heat of reaction. Okay, so the heat of reaction is a mathematical term in most cases, and we call it the delta, and this is a capital delta for change in, and we're going to write big H, and we're going to write the letters Rx in. Sometimes you just see delta H, many times you see delta H, but for me, I just want you to have Rx in there to kind of remind us that we're talking about the heat of a reaction. So the heat of a reaction, which is delta H Rx in, I'm going to immediately begin just using this right away. This is a quantitative description of the heat energy released or absorbed by the system. Now, if you've talked to people who are upper level chemistry and physics majors, I would say it's about 50-50 bag as to whether people enjoyed learning about thermodynamics. Again, these are people that want to study the hard sciences throughout their undergraduate curriculum. Only about half of them really enjoyed the idea of thermodynamics. I was on the fence. I did enjoy it, but it's I believe there's one major reason why people struggle to really appreciate thermodynamics as much as most scientists do, and it has to do with mathematical signs. Okay, when energy is released, we're going to describe our system as having negative energy. So a negative delta H of reaction corresponds to energy being released. Now you might think that's silly. Why would a scientist that wants to, dedicate an important chunk of their life thinking about this stuff get so put off by a field due to a negative sign and then conversely a positive sign? Well, if you're doing a bunch of math with the delta H of reaction, so a delta H of reaction that's positive is going to imply that energy is absorbed into the system. Well, if you're doing a lot of complicated math, like calculus and that sort of thing, using the ideas of thermodynamics, which is truly rewarding. It's a rewarding use of calculus. But when you're doing it and you do everything right except you have the negative sign wrong, it gets to be really frustrating. I've been there. It's true. So now that we have this, where a negative delta H of reaction suggests that energy is being released from our chemical system and into the surroundings, that's a negative sign. The energy is going down as it dissipates from the system. The energy of the system is going down. Whereas the energy of the system is positive or gaining when that energy is being absorbed. Okay, with that in mind, let's predict what is the sign of the delta H of reaction for combustion. And I'm going to actually, as you're thinking about what that answer is, I'm actually going to write the answer to more specifically, the delta H of the reaction of methane combustion, which is CH4, what we were looking at last time, equals 213 kcals per mole. Kcals, that's kilocalories, that's a unit of energy. We have to kind of normalize this per mole of methane that we put into the system, right? We could always have more and more. So having a standard unit, we just normalize everything and we say, hey, we're only going to use one mole of methane. 6.02, 2 times 10 to the 23rd molecules of methane, and we're done. No more, because any more would give us more energy, any less would give us less energy. Anyway, 213 kcals per mole. Now you're going to tell me, is that a negative 213 kcals per mole or a positive? Well, the energy in any combustion reaction is on the product side of the reaction. It's an exothermic event as the energy is being released from the system. And if it's being released, it's a negative sign. So this brings up another point. All exothermic reactions have negative delta H RXNs, negative delta H of reactions. Okay, so it's negative because the energy is lost from the system. Now we can't create or destroy energy in the universe, but we can transfer it from one system to another, system to the surroundings. Okay, so conversely then, all endothermic reactions have positive delta H of reactions. So they have positive heats of reaction as energy is gained from the surroundings. Okay, so I know I've mentioned these definitions a few times, but I guess I had plenty of room, but they're highly useful. One thing about the units, I'm just going to mention on the units again. People really like when they're talking about chemical systems to have whatever unit, whether it's kcals or I don't know, some other units. Kcals is a really common one. It's the only one I can think of right now. So whatever their unit is that they're looking at from a chemical system, oftentimes it is energy. So kcals or kilojoules or whatever, it's always divided by mole or per mole. And the reason why is anytime we do this, we have an energy unit or some other unit divided by a number of molecules. Remember, that's all a mole is. It's just some specified set number of molecules. What we get out is an intensive property. It's a lot like a density, where if you take the ratio of two extensive properties, right? So number of molecules, that's an extensive property. As you increase the size of your sample, you're going to increase the number of molecules you have. But if we set it to 1 mole, we've fixed the number of molecules. And if we fix the number of molecules, we can fix the number of energy that we can get in, or the energy that's required to be absorbed for a specific chemical system. So it's a really useful thing to do because it sets everything to be an intensive property. Okay, so thermodynamics deals with enthalpy, the amount of energy that's released, which is exothermic, or absorbed by endothermic by a chemical system. So again, we're thinking more broadly about thermodynamics. We're going to deal with enthalpy, which is the delta H, the heat of reaction. This is the energy that is released, which is exothermic, or absorbed, which is endothermic, by the system. Okay, that's not the only thing though. It's not just enthalpy, because then we would just, instead of calling it thermodynamics, we would call it enthalpy dynamic, I don't know, something. We would just refer to it as enthalpy. It's just the study of enthalpy. But it's not just that. It's also the idea of entropy. Entropy is a really interesting kind of property of a chemical system. Entropy is a measure of disorder within a system. And sometimes you can use more fun words like chaos, or less fun but more true words like randomness. So disorder, chaos, or randomness have to do with entropy. Now, in particular, what it's saying is that as you increase disorder, if something has become more disordered, it's more chaotic and it's more random. So as you increase the disorder, chaos, and randomness, you will then increase the entropy. That's how things are related. So increasing entropy means things become less ordered, more random, more chaotic. So as things become more, let's put it this way, more ordered, less random, that is, as patterns start to emerge, for example, entropy will do what? Well, entropy will go down. The value of entropy, however we quantify it, will now go down. Okay, so that's entropy. It's a level, it's a measure of randomness and disorder. So within chemistry, we can picture a few chemical events and think about their entropy. So what about phase transitions like boiling? Boiling, as you go from a liquid to a gas. Boiling or sublimation, anytime you go from a condensed state, which is a liquid or solid, to a gas state, you are going to increase entropy. So just looking at the physical kind of state of matter can give you some indication whether we're thinking about increasing or decreasing entropy. Similarly, freezing, here we're going from a liquid to a solid. So liquid, rolls, tumbles, fills the shape of its container, doesn't really have a fixed pattern. So liquid So we go from liquid to solid. Now solid, and many times it has a fairly regular lattice. Even an amorphous solid has some sort of pattern by which the molecules are sort of stacked and aligned to get to a solid material. So solids are highly ordered. Liquids can kind of roll, tumble, they're a bit more random. You don't need to be perfectly random, just more random. So as you're traversing from random to more highly ordered, you are now decreasing in entropy. So phase transitions can give us some idea. Now what about combustion reactions? These are chemical processes, not phase transition or physical processes. Combustion reaction, we're actually transforming matter. So let's say we have octane, which the great thing about octane in a combustion reaction, I mean, I know it's got some issues, don't get me wrong. But the good thing about it is that it's a fairly easy chemical to handle because it comes in the liquid state. That means it fills the shape of its container. It's not gonna like flow away to any appreciable degree while you're at the gas pump. So when you mix it with O2, you get CO2 in water, but this water is hot and in a combustion reaction floats away. So it turns out that if you just count the number of molecules in a balanced chemical reaction with octane, which is C8H18, I believe, we're actually going to form a lot of CO2 and a lot of water. That water is hot, so it's going to float away as gas. We're going to go from a liquid to lots of gas, a liquid plus some gas, to a lot more gas. Combustion is going to lead to an increase in entropy. Okay. So we can think about, based on kind of the physical states of matter, whether we're going to have an increase or a decrease in entropy. Entropy, though, is a little bit less intuitive than that in most cases, but still it can be measured. So we can measure the enthalpy, the amount of energy that's transferred from the system to the surroundings, and the entropy, the relative disorder or randomness within a system. We can measure both of those things, and we get to the idea of a spontaneous process. And a spontaneous process leads to a third way of describing the thermodynamics or the energetics of a chemical system. So a spontaneous process, these are kind of interesting processes that once initiated, and I'm going to put process / reaction, once they are initiated, they will go to completion and consume all limiting starting materials. Okay, so they will consume all limiting starting materials. Now, a combustion reaction is an example of a spontaneous reaction. Now, I was very careful in my wording here. Okay, if we have some octane, let's say we've got a pool of octane, and we start it on fire, it's going to burn and burn and burn unless we intervene. Let's say we don't intervene, though. Once it starts burning, it burns and burns and burns until all the octane is gone. Now, I know that we had two reactants. Do we consume all of the oxygen in the world? No, we are limited by the amount of octane. That is our limiting reagent. But once the octane has started burning, it will keep burning until that limiting octane reagent is fully consumed. And you can do similar things where you starve a system of oxygen, you see a fire deplete. But anyway, not about limiting reactions. I want to think about how this process just kind of keeps going and churning and churning and churning. Why does it do that? So what's special about spontaneous reactions? Spontaneous reactions are both exothermic, that is, they have a negative or a very low delta H of reaction, and they lead to an increase in entropy. So these are really good ideas to know, that when you've got a spontaneous reaction, it's some combination of being an exothermic process that leads to an increase in entropy. Okay, so we can describe this in a more quantitative sense using a term called the free energy or the Gibbs free energy. And I believe it's just become better to say Gibbs free, excuse me, energy. So Gibbs was an important scientist, and so we named the free energy after them. And so this is often called the delta G or delta G of reaction. It's a lot like the delta H or delta H of reaction, but it takes into account entropy. So this is, again, the Gibbs free energy. And delta G for a reaction is equal to the delta H of the reaction minus T times the delta S of the reaction. Now, I haven't talked about the delta S yet, but the delta S is the change in entropy. The change in entropy. T is the temperature. So just some temperature, and we have to care about the units. It's probably going to be Celsius. That's a good SI unit. So temperature, and then delta H, this again is the heat, and it's the change in, well, I mean, it's called the heat of reaction, and we'll just keep it there. Heat of reaction. Okay, I know there's a delta in front of that. We talked about what the delta means when we talked about the heat of reaction. It has to do with the change in energy that's being transferred out or absorbed in by the chemical system as it undergoes a chemical reaction. There's a delta in front of the S too, implying the change in entropy. We're always looking at relative entropy. What has more chaos and disorder, the starting materials or the products? Okay, so this equation gives us the delta G of reaction. So if we know delta H, if we know T, and if we know delta S, we can actually predict whether something is or is not spontaneous. So for a process to be spontaneous, the delta G must be negative. If that delta G corresponds to a reaction, sure, I'll call it the delta G of reaction. But for any process, if we want that process to be spontaneous, the delta G must be negative. Okay, now if we think about what makes something spontaneous, again, I said it before, we need an exothermic reaction, okay, releases heat into the surroundings, and we need something that has a high level of entropy. So if we think about the values there, a positive change in entropy, and a negative change in enthalpy or heat of reaction. So if we look at the equation up above, delta G equals delta H minus T delta S, okay? So T is always, right? And we'll probably use Kelvin. Okay, let's just say it's, I'm not gonna worry about it. I was about to say it's always positive. I think it is. I think you have to use Kelvin now that I think about it. So and Kelvin's just one of these temperature scales. It's always positive, doesn't have any negative numbers. So anyway, we always have a positive. I'm gonna write that. I'm gonna go on a limb and write that. It's been a while since I've had PChem, but I should know this stuff. And yeah, we use Kelvin because it's always positive. Goodness. Okay, so this is always positive, which means that if delta S is positive, and what that means is we have more entropy, and if delta H is, let's think about it now, negative. So I have a negative term here because, excuse me, let me point at it actually for you. So if I have a negative term here, because I said my delta H was negative, if I have a positive delta S, that makes this entire term here negative because T is always positive. If T is positive and delta S is positive, and we're throwing a -1 out in front of all of it with that minus sign, both of those terms, the delta H and then minus T delta S, are both negative. If they're both negative, delta G's got to be negative, and if delta G is negative, we're spontaneous. If delta H is negative and delta S is positive, we have a spontaneous process. And there are, different combinations we could have. Let's say we've got something that has a really low change in entropy, okay? Maybe even gets worse. Let's say it's a negative change in entropy. We make that term all of a sudden positive. So negative T delta S is now positive, delta S is negative. So this whole term over here is positive. That could outweigh the delta H term, and we could have a non-spontaneous process with a positive delta G. Okay, but that's sort of, entropy is a little bit temperature dependent. Okay, as you increase the temperature of the system, you're going to inflate that term more because temperature can help to kind of more increase the randomness of the system. But if you dial it back down, you decrease the influence of entropy on making a system spontaneous. Okay, what I'll just mention, just to kind of leave us with, is the idea of endergonic and exergonic. Endergonic, that implies a positive delta G. And exergonic implies a negative delta G. Now, what do these values mean? Like when we talked about exothermic, that meant heat was being released into the system, and endergonic, heat was absorbed. Does that mean that an endergonic system always has heat absorbed? Sometimes, okay? All I'm really saying is that delta G equals delta H minus T delta S, and in the case of an endergonic system, it's positive. It's all positive. The entire term delta H minus T delta S is positive if something is endergonic. And endergonic systems are not spontaneous. But in the case of an exergonic system, where we have a negative delta G, I'm not saying anything about heat being released, absorbed, or randomness or disorder. I'm saying this entire mathematical operation, delta G equals delta H minus T delta S, it's negative now. So it's negative. That's what I'm saying with an exergonic process. But if it's exergonic, it's spontaneous. Okay, so I'm going to end there. So thermodynamics is really looking at kind of the relationship of kind of the interplay, let's say, of enthalpy, which is delta H, and entropy, which is delta S in a chemical system. And including T in there, we get this equation, delta G equals T times delta S. And so using that equation, we can start to think about things like, is a reaction spontaneous or not? That's a really important idea if you're into chemical engineering, because if you're trying to engineer a giant reactor to help manage a system that's spontaneous, you don't have to work too hard. You just have to get the thing initiated and then contained. Whereas if you've got something that's endergonic or non-spontaneous, then you have to think cleverly about how you're going to add energy into the system to keep the reaction going. That's what a non-spontaneous process is. It needs the constant supply of energy to keep the reaction going. Okay, hopefully this was helpful.